Okay, ladies and gentlemen, let's continue with chapter 4. Chapter 4 is about transient heat conduction, and it has 4 sections. The first one was a lump system approach. The second one was transient heat conduction in large plane walls, long cylinders and spheres. We've completed both these sections, and the part we're going to do today is transient heat conduction in semi-infinite solids. And the last part will be, and we're not going to do that today, is going to be transient heat conduction in multidimensional systems. So let's start with paragraph 4.4, transient heat conduction in semi-infinite solids. What is a semi-infinite solid? Okay, the first thing we can say about a semi-infinite solid is that it is an idealized body. So there's not really something like that. But for the purposes of our study, a semi-infinite solid that we are going to work with is going to have 2 important characteristics. The one is, firstly, it's going to have a single plane surface. It's going to have a single plane surface. That is the first characteristic. And the second one, it is going to extend into infinity in all the directions. So in all the directions, it is going to extend into infinity. So those are the 2 characteristics of a semi-infinite solid. Let's show it schematically in terms of what we mean. What we mean is that this is the single plane surface. The single plane surface. This single plane surface, this is now the x direction, will extend into infinity. Okay. In this direction, it is also going to extend into infinity, and the same in that direction. So in all the directions, it extends into infinity, but it has a single plane surface, which is now this one that I'm representing here. And what we are interested in is the temperature change very close to the surface. So if I can show this single plane surface like that, and we extend the dimension into infinity, and this is the x-axis. What we are interested in is what would the heat transfer rate be in the x direction if suddenly this surface changes to a temperature Ts. So the whole body is at a temperature Ti. This big body that extends into infinity, very close to the surface, we're going to change the temperature to Ts. And we are interested, and that is very important, we would like to know what happens very close to the surface. Not very deep, very close to the surface. So in this area we are not interested in, because it should stay at a temperature Ti. Okay. Now let's consider this semi-infinite body. So we consider a semi-infinite body. we say that the thermal characteristics, the thermophysical properties are constant. So the K, the rho, the Cp, and all those things that we normally use of the body is constant. It is not changing. And we say there's no internal heat generation. There's no internal heat generation in the body. And where x is equal to 0, the temperature is equal to Ti at T equals 0. So the surface is equal to Ti. And the whole body is at the temperature Ti. And we are interested in the heat transfer rate only in the direction of the face. Ladies and gentlemen, can I ask you to be a little bit more quiet, please, while I lecture? Okay. That is what we're going to consider, and that is our assumptions. Let's start with the energy equation. The energy equation says partial d2t dx squared plus partial d2t dy squared plus partial d2t dz squared plus E gen divided by k is equal to 1 divided by alpha multiplied by partial dt dt. Okay, now in the derivation of this equation, the assumption has already been made that k, for example, is a constant. Okay, so that is the energy equation as was derived in this textbook of Cengel and Ghajar. Okay. Now in terms of what we consider, it has been given to us that the heat generation inside the body is equal to 0. So let's make this assumption 1. So that is assumption 1, takes care of that term. Okay. Then we also said we're only going to look at the heat direction in this direction. This body is so big that the heat transfer in those directions are not important, cannot be considered. So this is going to be our assumption 2. And assumption 2 takes care of those two terms. No temperature gradients in the y direction and no temperature gradients in the z direction. Everything changes only in the x direction. Okay, so we've got now a partial differential equation, and this partial differential equation says partial d2t dx squared is equal to 1 divided by alpha multiplied by partial dt dt. Okay, our partial differential equation. And obviously we want to solve it, and to solve it we need boundary conditions and we need initial conditions. Okay. First boundary condition is the temperature where x is equal to 0. Okay, where x is equal to 0, at that point there, is now going to change to a temperature Ts. Okay. So it was equal to Ti, and now at T equals 0, I'm going to change it to Ts. Okay. And maybe we should say here, it changes to Ts at T equals 0, and it was at Ti at T equal minus 0. Let's put in there a minus 0. Just before time equals 0, it was equal to Ti. Okay, so that is our boundary condition. So our initial condition would be that the temperature T at any position X at T equals 0, is equal Ti. Okay. The whole body was at a temperature Ti. So let's just show it schematically in terms of what we mean. This is the plane surface that we are considering. That is the infinite body in all the directions. And that would now be at T equals 0. And the same body at T equal T at any time after 0. This body at T equals 0 was equal to a temperature Ti, and this surface temperature was also equal to Ti. This changes now so that this temperature is equal to the surface temperature. Maybe a big body, and now it snows on the body. It is suddenly exposed at a temperature of equal to 0, and it was maybe at 15 degrees Celsius. And what we are interested in is to know, and I'm specifically drawing it very close to the surface, or relatively close to the surface, is to know what is the temperature as a function of T at any point. And if that is our X coordinate system, it would be a temperature at point X that we would like to know. And this temperature would obviously be the solution everywhere on point X from the surface. Okay. Now this equation that we have here is the same as that we had when we're considering a large plane wall. But the problem is our boundary conditions is now infinite. So the method of separation of variables cannot be used here. And we have to use another method to solve this partial differential equation. And this method of changing the partial differential equation to an ordinary differential equation. Okay, so we are going to change it. And we're going to do that by combining the two variables which are X and T, by changing it to one variable. So we've got two variables. We change it to one variable by defining a similarity variable, eta. So we define eta, where eta is now equal to X divided by the square root of 4 times alpha t. Okay. So from the two variables, X and T, we now only have one variable. And as you can see in this one variable, we've got X and T. Now if we use this eta and we say d2t dx square in terms of the chain rule, or let's just write down the equation first. That equation, partial d2t dx square is equal to 1 divided by alpha dt dt. And now let's go and look at dt dt, this term, in terms of eta. Okay. What we can do is we can make use of the chain rule and say it is equal to dt d eta multiplied by the eta dt. Do you agree? Okay. And the eta dt we can now differentiate that term. Okay. So it is equal to dt d eta multiplied by minus x divided by 2 times t multiplied by the square root of 4 times alpha t. Just the differentiation of that term. Okay. We are not going to do all the mathematics in detail because the next one is becoming a little bit more difficult. It is partial dt dx can be written as dt d eta multiplied by partial d eta dx, and that is equal to 1 divided by the square root of 4 times alpha t multiplied by dt d eta. Okay. If you can't see immediately where it comes from, just go and do it at home. Maybe I've made a writing error. So the small detail is not going to be important now. So just look at the principle of what we're busy with. Okay, so that would be for dt dx, but we actually need d2t dx square, which we can write as d2t dx square is equal to d d eta of partial dt dx multiplied by the partial d eta dx, and that is equal to 1 times 4 divided by alpha t multiplied by partial d2t d eta squared. Okay. Now look at the equation that we have. That is the one that we started with. Now we've got d2t dx squared is equal to this term. Is equal to 1 divided by alpha multiplied by that term, and that term is now equal to that. Okay, so if we do the substitution, we make it a little bit neat, we can now get an ordinary differential equation. d2t d eta squared is equal to minus 2 times eta multiplied by dt d eta. And now, what do we have? We've got an ordinary differential equation with one variable. And that one variable is equal to eta. Okay, how do we change a one-dimensional, an ordinary differential equation, a second ordinary differential equation to a first order one? We say, well, let's define W, which is equal to dt d eta. We just define W, and now we can make it a first order differential equation by saying that dw d eta is equal to minus 2 times eta multiplied by W. Okay. So if we say dw d eta, then we've got that term is equal to minus 2 times eta, and dt d eta, that term is equal to W. So now we've got a first order differential equation. Which we can solve. Not fully, but you will see. So let's move all the W's to this side and all the etas to that side. So dw divided by W is equal to minus 2 times eta multiplied by d eta. We can integrate that. That is equal to the ln of W is equal to minus eta squared plus a constant. Or we can say W is equal to C1 e to the minus eta squared, where C1 is equal to the ln of C0. Okay, now let's do a little bit of back substituting by taking W is equal to dt d eta and integrating. Then we can say that dt d eta is equal to C1 e to the minus eta squared. Where does this come from? From equation 1. From equation 1. W is equal to dt d eta. dt d eta is now equal to that. So dt is equal to C1 e to the minus eta squared d eta. And now, take note. The temperature, if we do the integration now, we get the temperature here, is equal to C1 multiplied by the integral of 0 to eta e to the minus u square du plus C2. Okay. Where does that now suddenly come from? Where u is a dummy variable. U is a dummy variable. Okay. Now we need to solve the constants C1 and C2. And in terms of this new u that we've defined, you're not going to understand immediately what I'm doing, but be patient. So the boundary conditions, the first boundary condition is at eta equals 0. Okay. At eta equals 0, when that is equal to 0, that would gives us the surface temperature. At t equals 0, and x would be equal to 0, then this temperature is going to be equal to C2. Okay. The next boundary condition is where eta is equal to infinite, the temperature is equal to Ti. Okay. And the other boundary condition, C1, can also be solved. The value is given in your textbook, you can go and do it at home. But the result of this is the following equation. T minus Ti, and if we substitute it a little bit and rearrange, divided by Ts minus Ti, this is again a non-dimensionalized temperature, is equal to 2 times the square root of pi multiplied by the integral from 0 to eta e to the minus u square du, and that is equal to what we call the error function in eta. Okay. The error function, or it can be written as 1 minus, take note, ERFC, which means the complementary error function in eta. So this is the error function, this is the complementary error function. Take a good look at it. I'm going to explain to you just now what is going on there. Okay, this term that I've identified there cannot be solved analytically. Cannot be solved analytically. Can be solved numerically. And this term is very similar to the sine and cosine function, which can also not be solved analytically. It's the result of a numerical solution. And the result of that can be plotted like that. So the error function as a function of eta typically from 0 to 3 looks like that. So this is the error function in eta, which is equal to 2 times pi divided by the integral from 0 to eta e to the minus u square du. So that is how that function looks like. And take note, when eta is about 2, the error function is equal to 1 for all practical purposes. Very, very close to that line, you see. Okay, where this eta, remember, is equal to x divided by the square root of 4 times alpha t. So if we want to get rid of that integral, we can actually write this equation as the temperature as a function of x and t minus Ti divided by Ts minus Ti is equal to the error function of x divided by the square root of 4 times alpha t. And in some cases you're going to look at it and then suddenly the 4 is a 2 and you're going to wonder now what is going on here. So it's very simple. You can also write it as the error function of x divided by 2. So the square root of 4 is equal to 2. You can just take it out. Is equal to alpha t. So whichever format you prefer, that you can use. Now these error functions, we don't need to use the graph. The use of the graph is not that accurate. In table 4.4, table 4.4, as you can see up there, the authors of the textbook, Cengel and Ghajar, gave you table 4.4. For different values of eta, they've given you, what do you see there? Take note, not the error function, but the complementary one. Okay. So it is just the opposite. It is the error function is equal to 1 minus the complementary error function. So, take note, it is the complementary error function which is given in table 4.4, which means the complementary error function, or the error function, is equal to 1 minus the complementary error function. So, for eta equal 0, the complementary error function, if you look at the table, would be equal to 1. So, if we want to calculate the error function, then the error function is going to be 1 minus the complementary error function, which is equal to 0. Okay. Another value would be typically at 0.5. At 0.5, the complementary error function is equal to 0.4795. Therefore means that is a complementary error function. The error function would be equal to 1 minus 0.4795. And if we look at the error function at 3, where eta is equal to 3, you will see that the complementary error function is equal to 0.402, which means that the error function would be approximately equal to 1. Okay, now that we've solved the temperature distribution, we can also solve the heat flux at the surface. The heat flux at the surface. So the heat flux at the surface would be equal to minus K partial dt dx, where x is equal to 0. And if we use those equations, do all the mathematics, it is very easy to show that it is equal to K multiplied by Ts minus Ti divided by the square root of pi alpha T. So that is the heat flux then on the boundary. Now for this problem, we've used a specific boundary condition. We said the body was equal to Ti, and at T equals 0, we take that surface and we change it to Ts. So in the textbook, there are solutions for other boundary conditions. There are solutions for other boundary conditions. And they are called case 1, case 2, case 3, and case 4. Okay. Now case 1 was the one that we did. That is where the surface temperature is changed to be a constant. Okay. And for that, the solution is summarized, and graphs and figures are given, and I'm going to show it to you just now. The second case is where the surface has a constant heat flux. Okay. So we take the plane wall, we do not change the temperature to Ts, but suddenly we've got a heat flux of maybe 30 kilowatts per square meter. There can be a chemical reaction, there can be an electrical resistance element, something like that. It changes the heat flux to a constant value on the surface. That is the second one. The third one is where the heat transfer coefficient on the surface is given. We change the surface temperature and there's a heat transfer coefficient. Maybe a wind blowing over the surface, or there's condensation or evaporation taking place on the surface, and the heat transfer coefficient is given. So that's the third one. The fourth one is an energy pulse, typically from a laser. And it gives a certain amount of energy which is measured in joules per square meter. So it's only a pulse at one point on the surface, And now we want to see how the temperature changes in the body. Now, if you look in the textbook, ladies and gentlemen, those are the mathematical solutions for the 4 different cases. There's case 1, where the surface temperature is constant. Case 2, where we've got a constant heat flux. So there you'll see in the equation, there's the heat flux that you need to put in. The third one is the convection at the surface. We've got the heat transfer coefficient. There you will see the heat transfer coefficient now in the solution. And the fourth one is the energy pulse with ES is equal to a constant, and there is ES in the solution. Okay. 4 different cases. The typical solutions can also be shown graphically. This is the non-dimensionalized temperature distribution for transient heat conduction in a semi-infinite solid whose surface is maintained at a constant temperature. So this is this first case that we've considered. And it can be plotted like that. So this is the non-dimensionalized temperature as a function of eta, and that would be the solution. The next one would be a block, a large cast iron block. The properties are given, the alpha and the K values, and this block is at a temperature of equal to 0. Okay. Now this surface is changed to 100 degrees. So a big cast iron block, we put it in an oven, and only the surface is exposed to a temperature of 100 degrees Celsius. So that would be how the solution would look as a function of time. So we can see that at about 400 millimeters from the surface, at 1 hour, after 1 hour, the temperature would be less than 40 degrees in this block. Okay. So that would be the solution for the first case. This is a solution now for the second case, where we've got a constant heat flux. The heat flux is 7 kilowatts per square meter on the surface. So the temperature is not constant, it's the heat flux that we put in that is constant. And again, it gives us the temperatures as a function of time. So we can see after 10 hours at a depth of about 600 millimeters, the temperature would be 40 to 50 degrees Celsius in that block. Okay. The next one would be where the heat transfer coefficient is constant. It's given as 220 watts per square meter, and the surface is kept at constant temperature. Again, there's the solution as a function of time. The fourth one is the energy pulse. The energy pulse, and this energy pulse is 1.7 multiplied by 10 to the 7 joules per square meter. The energy pulse, that is after a few seconds, that is how it would look like, and after a few hours, that is how the temperature distribution would look in the block. Okay, so those are the typical types of problems that we can solve by considering a body as a semi-infinite solid. This is also quite an important graph. This shows us how the temperature changes with position and time in a semi-infinite solid, initially at a temperature Ti, which is then subjected to convection to an environment at T infinite. So there's the environment at T infinite, the block is at Ti, the non-dimensionalized temperature as a function of eta for different values of H multiplied by the square root of alpha T divided by K. Okay. Sometimes it is convenient to use these graphs. Let's start with an example. I don't think we're going to finish it, but you can finish it at home if we don't. And this example is of a water pipe. A water pipe which is under the ground. And the soil has a thermal conductivity of 0.4 watts per square meter Kelvin, and alpha is equal to 0.15 e to the minus 6 meters squared per second. And this soil is at 15 degrees Celsius. Okay. The soil is at 15 degrees Celsius and there's a water pipe. And this is the distance x underneath the ground. Okay. Now, this is not going to be relevant to South Africa, but now there's going to be a snowstorm and snow, and the surface is changed, maybe in Siberia or something like that, to minus 10 degrees Celsius. So the question is, how deep must this water pipe be so that the temperature is not equal to 0? Okay. And the winter there can be 3 months. So it is, after 3 months, the temperature there shouldn't be 0 degrees Celsius. So we would like to know the temperature when that is going to be 0 after 3 months. Okay. 3 months would be, let's use 90 days. Okay, there are 24 hours in a day, and there's 3,600 seconds in an hour, and that would give us 7.78 million seconds. So after about 7.8 million seconds, the temperature shouldn't be 0. Okay, so let's calculate the non-dimensionalized temperature. The temperature minus Ti divided by Ts minus Ti is equal to the complementary error function multiplied by x divided by 2 times alpha t. Okay, something, ladies and gentlemen, that you should take a good look at is that sometimes this is Ti minus Ts, or that is Ts and that is Ti. Okay. And it looks as if there's a printing error in the textbook. But it has to do that with sometimes the error function is used, sometimes the complementary error function is used, and you can write it in different convenient forms. Sometimes you can get rid of the minus 1, etc. So just be careful. You'll see that there are differences. Okay. Now the temperature is 0 minus the environment temperature. The initial temperature is 15. The surface temperature is minus 10 and 15, and that should be equal to the complementary error function of x divided by 2 times alpha t.
That is exactly the same as what we've got on the bottom left over there, except that's error function of the complementary, but it's still Ts minus Ti.
Yeah. Just go and check. Maybe I've made an error here with the Ts's and the Ti's. Okay, so this is equal to 0.6. 0.6 is equal to the complementary error function of x divided by 2 times alpha t. And the result would be that eta is equal to 0.37. And we get that from table 4.4. If you look at the table, where eta is equal to 0.6, where the complementary error function is equal to 0.6, So if we look here at 0.6, we will see it is between 0.37 and 0.38. So eta is equal to about 0.37. Okay. So we can therefore say that x divided by 2 times the square root of alpha t is equal to x divided by the square root of 4 times alpha t is equal to 0.37, whichever format you want to use. Okay, x is what we want to solve. X is 2 times the square root of alpha, which is equal to 0.15, 10 to the minus 6, multiplied by the time is 3 months, 7.78 multiplied by 10 to the 6. That should be equal to 0.37, and that gives x as 0.8 meters. So the water pipe should be at least 800 millimeters underneath the ground to ensure that the temperature doesn't drop to 0 degrees after 3 months. We can also make use of the graph to solve this problem with. We can make use of that graph. You can go and write that. If you go and write it out, you'll see that is equal to the non-dimensionalized temperature of 0.6. There's 0.6. If you go and calculate the heat transfer coefficient multiplied by alpha t divided by k, you will see that it is typically that line, and if you go down, you'll see it is typically 0.37, 0.38. So that is an alternative solution method that can be used. Okay, ladies and gentlemen, thank you very much.